This discussion is presented by Grant Lobdell, General Manager, Dyne Fire Protection Labs. Our business specializes in laboratory testing to help fire protection contractors meet various inspection, testing, and maintenance requirements. Currently, we offer analysis for firefighting foam, fire sprinklers, antifreeze, and like today's topic, dry chemical agents. This presentation will examine a recent study here at Dyne Fire Protection Labs involving the dry chemical agent found in recharged portable fire extinguishers to determine whether they were in compliance with the current edition of NFPA 10, the standard for portable fire extinguishers. This presentation will examine the requirements of such agents, the analysis methods used here at Dyne Fire Protection Labs to determine compliance, and the scope and results of the samples analyzed. Note that any interpretation of an NFPA standard made during this presentation, and we will be discussing NFPA 10 throughout, shall not be considered the official position of NFPA or any of its committees, and shall not be considered to be nor relied upon as a formal interpretation. If you're looking for that formal interpretation, I would direct you to nfpa.org. To get started, let's look at the requirements regarding dry chemical agents and portable fire extinguishers. When you buy a new extinguisher, it comes from the manufacturer with the agent it was listed with. In the case of NFPA 10, the extinguisher would be listed, or in other words, evaluated with using UL 711, Rating and Fire Testing of Fire Extinguishers, and UL 299, Dry Chemical Fire Extinguishers. When it comes times for recharging, whether that be a teardown or after a usage, NFPA 10 gives us guidance on what can be placed back in the unit. NFPA states that portable fire extinguishers are to be recharged with the agent or agents that are specified specifically on the nameplate, or those agents proven, and I've put that in red as you can see on screen, proven to have equal chemical composition, physical characteristics, and fire extinguishing capabilities. So unless you're going to prove an agent other than that listed on the nameplate is of equal chemical composition, physical characteristics, and fire extinguishing capabilities, which would be quite costly. Again, we're basically talking about redoing the listing test, including a full-scale fire test to do that. You're basically going to be using the agent that's listed on the nameplate of the extinguisher. Topping off a reusing agent is certainly allowed. You can reuse agent, provided you thoroughly, again highlighted in red, check that the agent being reused is of proper type, contamination, and condition. And we'll get into each of these type, contamination, and condition shortly. And we'll even talk about whether or not visual inspections are thorough or not. So is this occurring? Are people recharging extinguishers with the agent that's listed on the nameplate? Are they thoroughly checking any reused agent for proper type, contamination, and condition? This is something that many of you may have thought, or in the industry as a whole, but Fire Technology Innovations came to us looking for answers to these questions. They funded and provided the samples at the heart of this discussion today. So they pulled 100 different ABC fire extinguishers from service that had previously been recharged and asked us to determine if the agent inside them matches those NFPA 10 requirements. Mainly, isn't the agent listed on the nameplate? The samples represented 82 different organizations, and these are organizations we frequent every day, from retail locations to dining, from lodging to transportation. The samples represented 50 different fire extinguishers service providers as well. So we're not looking at any one provider, whether they're doing it right or wrong. We're looking at the practices of the industry as a whole. So this study included 9 different extinguisher brands as well, and various sizes and ratings. If you want any more detailed information on the samples in this study, please contact Mike Friedman, Managing Director at Fire Technology Innovation. His email, where you can contact him, is found on screen. So to try and get these answers, try to answer these questions, whether or not the 100 extinguishers pulled from in service had the agent listed on the nameplate, we decided to look at 3 things. One, obviously, being the chemical composition. That's called out right in NFPA 10 of equal chemical composition, or the proper type. We also wanted to look at something with physical characteristics, and we chose to look at particle size. So has the agent lost a significant amount of its fines or not? And we'll get into that. We also decided that we needed to look at the agent from an ITM perspective and whether or not it had been contaminated, if it was free of moisture, at an acceptable level of moisture. So these are the three key benchmarks we are looking at in this study. So by no means is this every test that's done as part of the listing or any test that could be done. These are just a few key benchmarks. Typically we'll be asked whether or not a product still works. And works is obviously a loaded question when they ask it. I mean, whether or not something works, we're talking about those listing standards. So UL 711 or UL 299. So for us and all the ITM services we provide, we're really looking at a few key benchmarks to kind of evaluate, does a product still look like the product that was listed with the equipment? So of those key benchmarks we're going to look at in this study, again, chemical composition, particle size, and moisture analysis. Let's start with moisture analysis. Here at Dyne, we determine the moisture content in a dry chemical sample using Karl Fischer titration. Essentially, we're pumping dry air over the sample of the agent while it's exposed to heat. That heat or that sample placed in the oven, it's going to force the moisture from the sample into the dry air, and that dry air being pumped over it is being collected and quantified via chemical reaction in the back of the instrument shown. So it's a very sensitive test, and we're capable of determining as little as 0.01% moisture in an agent that we received. So let's get into the moisture requirements now. Unfortunately, UL 299, which again is that listing standard, in there they do not set a quantitative requirement on moisture content. There is a drop test discussed when they are testing whether or not the agent has a tendency to absorb moisture from the air or not. So this drop test is simply if you have a caking, if you have a lump, dropping it from a certain height onto a hard surface and seeing if on impact if it spreads apart or not. But we really wanted something more quantitative here. So for that, we looked to ISO 7202, another recognized standard, which is really geared towards specifically the chemical and physical properties of a dry chemical agent. So whereas UL 299 is geared toward the agent and the equipment combined, this standard ISO 7202 is really geared toward the physical and chemical properties of just the agent. So ISO 7202, and what we're going to talk about of the three tests today, this is the only one where it's fixed. It doesn't matter the brand, doesn't matter the type. It's fixed, the requirement for moisture. You have to be equal to 0.25%. So if I have any moisture greater than 0.25% by mass in any of these samples, it would be deemed unacceptable. So that is the moisture requirement. So what's shown on screen kind of gives you, and that 0.25% is a very low number. What's shown on screen gives you kind of a visual representation of how little that is. On screen, I believe it was a gram of sample. We took a moisture droplet, put it right on there, and that kind of gives you a sense of that would be 0.25%. So it's not a lot of moisture. You can imagine, too, if that moisture was spread throughout the whole sample, it would be quite hard to detect via visual inspection. So an agent with moisture spread throughout is probably not something you're going to see in a visual inspection. An agent with high moisture content is going to lead to caking of the agent like we talked about. So that's going to prevent the flow of an agent and maybe even blockage. If you've ever grabbed an extinguisher, squeezed the handle, and nothing came out, it could be caking that is the cause. High moisture content can also lead to corrosion of various pieces of the equipment, leaving them either inoperable or even dangerously weakened. So a shell that's experienced corrosion under pressure obviously could explode and be a health concern. So that is the requirements for moisture. Getting to the actual results of the 100 samples we received from previously recharged extinguishers. Again, these are all in service out in the field. 45 of the 100 samples analyzed, or 45%, actually had a moisture content above that acceptable level, above 0.25%. So where did this moisture come from? Well, you can certainly have moisture produced when mixing incompatible types, ABC and BC. Someone may have mixed those two agents and it can form carbon dioxide and water as the byproduct. But I tend to think the industry as a whole understands that we should not be mixing different types. So I don't think that is the main source. I think what could be going on here is maybe when we are going to reclaim these agents, are we using those closed recovery systems that are required by NFPA 10? Without those, and if the system is not truly closed, we could be exposing it to moisture in the atmosphere or other sources. So we want to make sure that we're using those closed recovery systems as designed. Again, on screen is a way to demonstrate whether or not a visual inspection is thorough enough. We show on screen we have one agent that contains 0.08% moisture and one that contains 0.45%, obviously unacceptable at that 0.25% cutoff. Can you tell by a visual inspection which one's acceptable and which one's not? I can't. I don't think you can either. And again, this shows the visual inspection may not be thorough enough to determine whether the moisture content is acceptable or not. So almost half failed that we saw. Again, these are all in service, these 100 extinguishers, almost half of them had an unacceptable level of moisture, had contamination. So moving on to chemical composition, the second of the three benchmarks we looked at Dyne Fire Protection Labs. We analyzed the chemical composition of each sample using a combination of ion chromatography and an acid-base titration. So with ion chromatography, we're going to put the sample in an aqueous solution, then we're going to run it through a column. And this column is designed to separate out the different components, or ions in this case. So essentially each ion is attracted to the material in the column differently. Some are more attracted and they'll travel slower. Some are less attracted and they'll travel faster. So let's say sodium is less attractive, it flies right through that column. But ammonium maybe is more attractive, takes a little bit longer to come through. So we started at the same, they were all combined in our solution, but coming off the column we were able to separate, isolate, and quantify them. So that's essentially how the ion chromatography works. For the acid-base titration, we're really just looking at carbonate here. And the carbonate obviously is found in BC agents, that's your sodium bicarbonate, your main ingredient there. Purple K agents, your main ingredient being potassium bicarbonate, but it can even be found in some ABC agents, a very small amount of calcium carbonate. Luckily for us, that carbonate is really the only basic compound in these agents. So simply adding acid to that aqueous solution of sample, we can monitor that acid-base reaction. The amount of acid needed to neutralize that base is related to the amount of base to begin with, or the amount of carbonate. So that's how we're analyzing the chemical composition of these dry chemical samples. For requirements, again, UL 299 does not give us any guidance here. UL 299C does have some methods for determining the composition, but they don't set any requirements. So what UL 299C, okay, they're analyzing this data. What they're doing is the sample worked. What is it now? Okay, every single one coming off the assembly line should match that. So same thing here. When we're going to analyze these chemical composition, what are we comparing it to determine acceptability? We're comparing it to the manufacturer's declared. They've listed the agent, they've said it's 90%, for example. We want to see a 90% agent here. But obviously there must be some variance allowed, and here's where we look to ISO 7202 again, where they do have requirements on the allowed variance. So for a product, for example, a component greater than 65, it says plus or minus 3%. So my 90% MAP products out there, I'm allowed anywhere from 87 to 93%. So if they advertise a 90% product, here at the lab I found 89 or 91, still acceptable, and that would be reflected in the results we're about to talk about. So agent with a different chemical composition would obviously, one, it's not going to be an agent listed, it's not on the nameplate, it's not listed with that equipment, that's a problem, seeing as it's a requirement from NFPA 10. And two, it may not perform as designed. Agents are formulated for specific hazards and ratings. Changing that composition, even slightly, could lead to poor performance. Or in extreme cases, if I mix two agents, two different types, ABC and BC, a chemical reaction, which could be dangerous. But even mixing agents of the same type, two ABC agents, let's say I have a 90% and a 60% product. Well, if I mix those, now maybe I have somewhere between 70 and 80%. I no longer have either product. I no longer have an agent going in a piece of equipment that it's listed for. I no longer have an agent that's been evaluated with that equipment. So that can be dangerous as well. So let's get to the results. We saw with the moisture, the 100 samples, almost half had an unacceptable level of moisture. Even worse results here for chemical composition. 87 of the 100 samples analyzed, almost every 9 out of 10, had a chemical composition other than that listed on the nameplate. So it was outside the range, the acceptable range, again defined by the manufacturer and allowances by 7202. So that's quite a bit. Like I said, almost 9 out of 10 had a composition that differed from the nameplate. And people always ask me, they're always concerned about low MAB content, even though low MAB, 60% products just fine if that's how it's listed and rated for. But people often ask that. That's shown on screen. Almost half of them, 43 out of those 87 failures, had low MAB content. So the other half would have had high MAB content. So again, how does this occur? Again, either the correct agent isn't being used outright, we're refilling it with something other than what's in the extinguisher, or we're inadvertently mixing agents. So for an example on how you can imagine this, imagine you come out to my site here, my laboratory, and I have a couple different types of extinguishers, let's say 2. And one of them is a 90% product, and one of them is a 60% product. If I come out and I take both of them back to my truck and I dump, I use my closed recovery system, dump them all into the same hopper, well, I've mixed the two, right? So I don't have either product that's listed on that nameplate. Had I done each separately, I've done either the one or all of them that are that 60% product, that exact product, and then done the others, I wouldn't have mixed them. And I think that could be what's occurring here, especially when we're seeing both highs and lows. On screen, we're going to talk briefly about the visual inspection. And this is another demonstration. Can you tell which agent? So I'm showing 2 agents, one 92% MAP product and one a 55% MAP product. Can you visually tell which is which? And hopefully you know which one you need. And no, you can't. If I need the 90% MAP product, I can't tell which one's the 55 and one has the 92. So a visual inspection, again, would not be thorough enough. So that gets us through 2 of our benchmarks. We went through moisture, about half, again, had unacceptable, higher than 0.25%. This was the chemical composition. 9 out of 10 had a composition that differed from the agent listed on the nameplate, half of those being low MAP content. And now we'll get into particle size, the third, the physical property we looked at. So for this, we're going to use a sieve shaker. So a sample of the agent is placed on top the nest there of sieves, those silver sieves stacked up. And it's going to shake and tap the nest there when I put agent on top and try to force it through those sieves. And anything smaller than the sieve openings, it'll fall through. So the openings of each sieve, it gets smaller and smaller as it works its way down. So any particles collected on each sieve are measured by mass, and we're able to quantify that. So typically we're going to talk about this as a distribution. So I'm going to talk about I have X% at this size. So for example, a manufacturer might say I have 20% of my agent should be greater than 63 micrometers, something like that. So any particle that is able to make it all the way through all these sieves, these fines, is going to be collected at the very bottom in a pan, and that is also masked. So for our nest of sieves, and I've shown on screen the sizes we use, and it actually accounts for both the ones mentioned in UL 299C, but as well as ISO and EN. So it accounts for various standards. Typically each only uses 3, but we're able to do them all, and whatever you need, we can account for it. Our lowest one being 40 micrometers. So anything in our pan, everything that is able to fall through there should be less than 40 micrometers. So let's look at our requirements. Again, UL 299 doesn't really set a requirement specifically. They don't say X amount needs to be this size or Y amount needs to be that size. Again, they're looking to see, does it work? Does it pass the fire test? Does it pass all the other tests? And if so, 299C, again, does have a method to collect this information. But again, they're just going to use that information to compare it to everyone coming off the lot. So acceptability for us, again, for this study, is going to be manufacturer declared. If they said, hey, 20% needs to be at 125 micrometers, that's what we want to see here. But again, what if it's 21%? Is that acceptable or not? That's where we're going to look at ISO 7202. That gives us our acceptable ranges. So again, if I said 20% needs to be at 125 or greater, I could be anywhere from 15 to 25%, and that would still be acceptable for this study here. Agents with a different particle size distribution could lead to issues with the agent flowing as designed or not. So as you can imagine, if an orifice is designed to flow a particle of a certain size, if you increase that size of that particle, it's not going to flow through that hole very well anymore, maybe even blocking it. So another importance, and that is what is shown on screen now, is the fines, those less than 40 micrometers in our test here, those fine particles and their fire extinguishing capabilities. So on screen is a graph pulled from a Naval Research Laboratory paper showing the extinguishment effectiveness versus the particle size. And on this, they're showing these different lines are all different products. I have a monoammonium phosphate. I have my potassium bicarbonate, my potassium chloride, different types of agents, and all of them show a significant decrease in effectiveness at that 40 micrometer mark. So these fines are what are really giving us our fire extinguishing capabilities. So let's look at the results then. The third benchmark of our test, 96 out of 100 had a particle size distribution that would not meet the requirements, be found unacceptable based on the requirements we talked about. Almost half of those, almost a quarter of those had less than 50%, less than 40 micrometers. So a quarter of those didn't have a majority of fines. Whether or not that's acceptable or not, people ask that, but again, getting back to our distribution, what's acceptable or not, 96 out of the 100 failed to meet the requirements. So what's on screen now, you can see a drastic example. This is something a visual inspection could certainly identify, these large foreign objects, these pebbles, but that's not always the case. The distribution, whether or not I have 20% or 40% at 63 microns, you're not going to be able to see. Again, getting to whether or not visual inspections is sufficient, is thorough enough. So in conclusion, we went through 3 benchmarks. Again, FTI sent us 100 samples. In these 100 samples that were sampled from in-service, they were recharged previously. We had half of them fail for moisture. We had basically 9 out of 10, so 87% where it was the exact number, have a chemical composition that differed from the nameplate. And then we had 96% with the particle size distribution fail. In total, none of the samples would have met, not a single one would have met all 3 requirements. So those that met the moisture requirement maybe didn't meet the chemical comp. Some that met the chemical comp didn't meet the particle size requirements. So they're all usually a combination of some of them, or some products even failed all 3. So this is unlike anything I've seen in terms of the ITM test, at least for the products we do, the fire protection products we do here at Dyne. For firefighting foam and sprinklers, even antifreeze, the failure rates are generally below 5%. So foam, that's less than 5% fail, and we see that every year they got to sample it. For sprinklers, it's spread out more. It's every 10 years or after 20 or after 50. But again, the failure rate's generally quite low. So this is certainly something I'm not familiar with, I have not seen before. This is quite high, not a single one. Would pass all 3 of these 3 benchmarks we looked at. Certainly they might not pass other tests as well, but we've already shown them to have issues. So if these samples are representative of the industry, then there's a lot of extinguishers out there that have been recharged with either a mixture of agents or not the agent that's on the nameplate, but in either way, it's filled with agent that's not listed with it. And that is a big problem. That's currently a requirement that's out there. So if that's important, and obviously some people felt it was important to make it a requirement now, the industry really should look at the process for recharging, how we're inspecting these periodically, and enforcement. So I appreciate you watching. If you have any questions related to the analysis done as part of this 100 sample study, again, we did the chemical comp, the moisture, and the particle size. You can reach out to myself, Grant Lobdell, General Manager, Dyne Fire Protection Labs. My email is shown on screen. If you have questions related specifically to the samples that FTI provided or specific results, you can reach out to Mike Friedman, Managing Director, Fire Technology Innovations.